Okay, now let's talk about something else that's also very important. Has anybody heard about systolic arrays? 1, 2, really? Who has not heard about systolic arrays? Don't be shy. Okay, that's good or bad, I don't know. Hopefully it's good because now you'll learn something. Okay, so this is actually also a fascinating concept. But before I go into systolic arrays, I wanted to put a pitch for the seminar course and also reduce the intensity of the lecture a little bit. Basically, if you're interested in computer architecture, I'm offering Bachelor seminar in computer architecture actually throughout the year, fall 2019, also spring 2020, I guess, next time, since we're 2019 today. So this is a rigorous seminar on fundamental and cutting-edge topics in computer architecture. So if you're interested in things like what we just discussed, this is for you. It does take some work, basically critical presentation, review, and discussion of seminal works in computer architecture, and also a lot of cutting-edge works also. So we cover things like hardware security, for example, but also fundamental paradigms. And yeah, you can see this over here. Everybody needs to take a seminar course. So if you're inclined for computer architecture, I would definitely recommend that you take this course. But there are limited spots. Okay, if you're interested, you can look at the past year's course and what kind of topics are covered. We're not going to cover exactly the same papers, of course, but there may be some overlap. And also, I think more generally, if you're interested in learning more or doing research in computer architecture, I have 3 suggestions. If you're interested, email me and CC Juan. That usually helps. Redundancy is always good for fault tolerance, as you know, right? Packets get dropped, but if you have redundancy in terms of time as well as space, you minimize the packet loss probably. And I would recommend taking the seminar course also because that would enable you to gauge your interests. There's also a more advanced computer architecture course that's at the master's level, but a lot of bachelor students also take it. And I would also recommend doing the readings and assignments on your own. And if you're interested, there are many exciting projects and research positions available that I have in my group, and I like working with undergraduate students. Actually, if you look at the Rohammer paper that we've done a few years ago, there were 3 undergraduate students involved in it. One of the undergraduate students is a PhD student with me right now, Jeremy, but he was an undergraduate student when actually he worked on the Rohammer project. So I think as an undergraduate, if you're inclined to do so, I would recommend enhancing your experience in different ways. And one way certainly is doing research, and you have the environment to do so at a university like this. So if you're inclined to do so in that direction, definitely go toward that direction. If you're inclined to do so in some other direction, do that also, like entrepreneurship, right? If you want to become an entrepreneur, do it that way also. So I think at the university level, don't just take classes, focus on exams. I know you need to pass the exams in the first year, sure, but also focus on other things that enable your development. Because as we will see, nobody remembers your exam scores from 30 years ago. Okay, but basically, there's a lot of exciting projects in memory systems, hardware security, GPUs, FPGAs, heterogeneous systems, and new execution paradigms like in-memory computing. I'll try to squeeze in a lecture at the end talking about this, because this is really important, I think. You should be familiar with the paradigms that are coming forward as opposed to paradigms that are looking backward. And also, there are clearly many trade-offs today in security, architecture, reliability, energy, and performance. So we cover a lot of these topics. And we cover a lot of these topics in the seminar course also. Some of the topics will be architecture for medical, health, and genomics. So I said a lot over here, but you can read these slides. And if you have interest, definitely don't be shy. Contact me, contact Juan, contact both is better, or multiple people is better. Okay, that's the end of the advertisement. Now we can continue with the broader agenda. But hopefully the advertisement is very much related to the broader agenda, right? Clearly I'm doing this because I'm excited about doing this. I wouldn't be spending my life and having a lifestyle of research if I wasn't excited about doing this. So if you're excited about doing it, you should just do it. And excited about doing X, you can replace that X. If X is research, that's great. If X is, I don't know, doing nothing, that's also great, right? Just but of course, you should be comfortable with that. That's the key thing. Okay, so we've covered all of this, and we're covering other execution paradigms. And now we're going to cover systolic arrays. This is actually a fascinating topic, I think. I was covering this in my lectures before they became extremely popular. And you will see why they became extremely popular. There's a good reason. And when I was covering, I always thought it was very fundamental. It was basically too important not to cover. And maybe other people were questioning the fact that, why are you covering this topic? I mean, nobody implements them in large scale. But it was, for me, it was too important. It was a very principled design. And I think the fact that I covered it was very helpful for the students who took the courses, because now everybody uses systolic arrays for machine learning, essentially. Okay, so readings for today. I didn't advertise these readings before, but I think it's better if you read this seminal paper by H.T. Kung, Why Systolic Architectures, that was written 37 years ago, as you can see, that talks about systolic architectures. It's required. You can read it after the lecture, but I'm going to essentially give an overview of that reading. And this is a recommended reading, which essentially uses the principles that were developed in this paper to design Google's tensor processing unit. They basically design a very limited form of the architecture that was proposed here to accelerate neural network computations in Google's data center, basically. And they basically find that, according to them, they can outperform GPUs, for example, by 80x. That's almost 2 orders of magnitude. That's their claim, though. I'm sure NVIDIA has some other concerns about that, and they have a different claim. Okay, but related to that, we're going to talk about that as well. Basically, there's readings for next week. Next week, we're going to transition to GPUs. We're going to talk about them, and this is a required reading. It's going to be not so easy to read, but I think it gives you an exposure to this. There is no perfect reading, unfortunately, in this area, unless you're going to read a 300-page book, and I don't want to assign a 300-page book. And even that book doesn't cover the material as I would like to be covered. And there's also a recommended reading over here that talks about MMX technology. So you will see that the importance of SIMD, single instruction multiple data, has influenced general purpose processors as well, not just GPUs, but general purpose processors. And this was the seminal work that introduced single instruction multiple data extensions to the Intel architecture. And there's a good story that I will tell you about it when we cover it. Okay, so let's talk about systolic arrays. Let me introduce the concept before we go into the break. Basically, the motivation was, this is going to be very different from whatever we covered so far. The closest form is really data flow, but it's, again, not data flow. So essentially, the goal was to design an accelerator. We don't want to design a general purpose machine. We want to design an accelerator that's specific for particular tasks. And what do we want here? We want simple, regular design so that the design is easy. So philosophy is, again, similar to VLIW a little bit, but it's going to be very different. So we want to keep the number of unique parts small and regular. We want high concurrency, because the problems that we're going to look at have a lot of parallelism, and we want to exploit that parallelism to get high performance. And we want to balance computation and I/O bandwidth. It turns out memory has always been a problem, and it's a bigger problem when you have a lot of data. So you don't want to, if you look at a general purpose processor, you basically load one element of data, do something on it, and store it, right? You don't want to do that, basically. You want to basically, with one element of data, you want to do many things until you store it. And that's the idea over here. So the idea is actually very simple. You replace a single, it's actually a very general idea, but we're going to see a specific example, and then we're going to generalize it. So let's start with the general part. You replace a single processing element. Processing element could be a specialized functional unit. It could also be a processor, but let's start with the processing element. With a regular array of processing elements, and carefully orchestrate flow of data between these processing elements, such that they collectively transform a piece of input data before outputting to memory. So you take a piece of input data, do X on it, Y on it, Z on it, T on it, U on it, ... Maybe you do 100 different things on it before you put it back into memory. And you have all specialized things, processors, to do that, or processing elements. So the benefit is now you're maximizing computation done on a single piece of data element brought from memory. So this is the example from the paper that you're assigned. Essentially, if you look at this system, you have a single processing element, and you pay the cost of 100 nanoseconds to access memory every time, as opposed to outputting the data back into the memory and getting it back again and doing something on it. Why not do this? Basically, this is the systolic array. Essentially, you take the data, this element does something on it, passes to the next element, that element does something on it, passes to the next element, that element does something on it, passes to the next element, ... Now, this is conceptual at the very high level, right? PE can be anything. PE can be a single processor. PE can be, again, multiple processors inside. PE can be a very simple function, as we will see, that performs essentially multiply and add. So it could be generalized. That's why the concept is very powerful. Why is it systolic? Well, systolic is about the heart. Basically, memory is, in this case, the heart. That's where the data gets pumped. And data is the blood. And processing elements are the cells that take the blood and do something with it. Right? That's the idea over here. So memory pulses data through the processing elements. And as you know, we have veins that connect our cells with the heart, right? And essentially, that's the inspiration over here. And you can read the paper. So basically, data flows from computer memory in a rhythmic fashion, passing through many processing elements before it returns to memory. And you carefully orchestrate the data flow when you actually program these machines. We will see examples. So it's similar to blood flow. You basically have heart pumping blood to many cells, and the data goes back to heart, and then you pump again. So different cells actually process the blood, and many veins operate simultaneously. So the heart doesn't get connected to different cells separately, right? There is a network in which these cells get connected to each other. And this could actually be many-dimensional. That's actually true in human body also. And as we will see, many-dimensional arrays could be useful because you may have different types of data coming in. For example, if you're doing a matrix multiplication, you have elements X coming from this dimension, elements Y coming from this dimension. So it makes sense to have a two-dimensional array of processing elements where each processing element can basically do the multiply and accumulate and pass the data to the next element. And then they all concurrently operate, and data eventually, the outputs flow at the bottom, for example. Okay, so why essentially special purpose X-rays architectures need whatever we discussed earlier: simple, regular design, high concurrency, and balanced computation and I/O bandwidth. So the basic principle is to replace a single processing element with a regular array of processing elements and carefully orchestrate the flow of data between these processing elements. And this balances computation and memory bandwidth because you fetch the data once and you do many operations on it, as opposed to fetching the data once and doing one operation on it. You basically, memory bandwidth is valuable, so you basically make use of your memory bandwidth as well as possible. Right? So you may say, okay, this looks kind of like pipelining. It does kind of look kind of like pipeline, but the concept is very different. Essentially, these are individual processing elements. They're not stages of instruction execution. These are processing elements that do an entire operation on the data element. Right? That's one difference. The second difference is, even though this is linear, a systolic array could be multidimensional. It could actually be triangular. It could be two-dimensional, and it could be three-dimensional with three-dimensional stacking technologies going into the future. And the connections between processing elements can be multi-directional, as we will see. So here, the connections may be linear, but if you have two-dimensional processing elements, maybe you're connected to all of your neighbors, for example, right? And then you somehow orchestrate the data flow. And it could be different speed. And also, again, different from pipelining, each of these can do operations, so it can have local memory, very simple memory structures, and execute kernels as well, rather than a piece of the instruction. So in pipelining, you're really executing a piece of the instruction in these pipeline stages. They're not processing elements. Okay, so let me give you a computation example. I'm going to take some time, and then we're going to take a break, and then I'm going to continue. So how many of you know about convolutions? Anybody? Who doesn't know about convolutions? Okay, you should really take a machine learning course. At some point, you'll take a machine learning course, and you will learn about convolutions. When I was teaching the systolic arrays, these convolutions are not as popular at that time. But convolution is essentially an operation that you do on two functions. You convolve one function with another function, and essentially you get some output. This is used in filtering, pattern matching, correlation, polynomial evaluation, many image processing tasks. And actually, machine learning uses convolutional neural networks a lot. And I'll give you the story before we take the break, so that in the break you can discuss maybe how cool this is. Okay, I'll take 5 more minutes. So basically, because this is cool, and I think you'll like it. So basically, in machine learning today, you have up to hundreds of convolutional layers in convolutional neural networks. So what is convolution? This is the mathematical definition. If you go to Wikipedia, you'll find the same definition, basically in a different way. Given a sequence of weights, and the input sequence, you basically compute a result sequence this way. You basically convolve the input x with the weights, and this is the mathematical definition. You basically do some sort of filtering, in a sense, when you do convolution. You basically transform the function in a different way. you can think of this as you basically have some weights, and you're basically look at some inputs, and you're basically checking how these inputs and weights somehow match. Okay, so, and where this is used, for example, this is one example of an image recognition network. It's called LeNet, and it's a convolutional neural network. Basically, the input is an image, and you take the image, partition it into some pieces, and take it through some of these convolutions through some weight vectors. So let's assume that you've somehow trained a network, and you know the weights. You know what different parts correspond to what different parts of an image potentially correspond to different weights. You take the image, you run it through the weight vector, and that weight vector somehow identifies what this part of the image looks like. And then that's one convolutional layer. So this produces some convolution results, and then you sample them in some way, and then run it through more convolutions, sample them in some other way, run it through some more convolutions, and then at some point, you decide based on all of these mathematical operations that you do that you have an A at the end and not an E at the end. So this is a basic example of a convolutional neural network. Again, I'm not going to go through how this exactly works because that's not the purpose of this course. In a machine learning course or a computer vision course, you can easily figure out how this works. But basically, you have some number of weights that you've learned based on training with many, many images. Those weights are used for convolving different parts of the input image such that you kind of start guessing what does this image look like. And eventually, if you somehow learned that this overall image looks like an A, hopefully this will output an A. If this is a cat, this will output a cat, right? Or maybe the type of the cat. It all depends on how you configure these weights. And these weights are essentially these weights over here. And the input sequence is the image, part of the image that you're looking at, and the result sequence is the intermediate output that you have over here that you're going to do some more processing on. But this is an example neural network, convolutional neural network that is used for identifying images. And if you go to Jan LeCun's website, you will see an example over here. But basically, you can read this. Convolutional neural networks are designed to recognize visual patterns directly from pixel images with minimal pre-processing. They can recognize patterns with extreme variability, such as handwritten characters, and with robustness to distortions and simple geometric transformations. All is done by training this multi-layer network such that you learn the weights. And then this is an example of operation of a convolutional neural network. And you can see the different layers, what they output over here. So you can see that it is recognizing the characters. But if you want to learn more, you can look at this. So it turns out you can implement this convolutional layer with matrix multiplication. We're going to see that. And that's exactly what Google does in their systems. This is a convolution filter over here, and this is the input. And you can turn this into a matrix multiplication. I'm not going to go over this. You can take a look at it. But I'm going to give you a story before we finish. So the reason why these things actually became extremely popular is because of the processing power that we have today. We will learn about GPUs next week, but the convolutional neural networks were very popular at the University of Toronto. Jeff Hinton was actually one of the proponents of it. He was one of the early developers of neural networks. And some of his students actually took the class that was taught by a computer architect, Andreas Moschovos. And what they did was, this class was about programming massively parallel processors. And these students developed the GPU implementation of a deep convolutional neural network that was trained with 1.2 million images at the time. And by doing a GPU implementation, a very good GPU implementation of that network, they were able to win the popular ImageNet competition, which became even more popular after that. And if you're really interested, you can read the paper that they wrote about this. They basically showed that they were able to improve the accuracy of image recognition by about 10 to 11% compared to the best previous approach by using the power of the GPUs. And you can read this paper. It's actually a really nice paper. I think it's had a lot of impact in the field in the last 7 years. And then later, this led to other people trying to improve accuracy. Google actually improved accuracy by adding more layers to the network. The network that I showed you had 5 layers, I think. Google increased it to 22, for example. And they showed that they could improve accuracy even more. And then you saw a lot of other papers that improved the accuracy. As you can see, this is one of the other examples of networks. So very quickly, today's networks have actually a lot of layers. Like some of them have 152 layers. I think that's ResNet, this paper over here. And they're more accurate in recognizing images compared to humans. Basically, human recognition is error rate is about 5.1%, and the machine error rate is about 3.5% in ResNet. And today, actually, it's even better. I don't have the latest over here. But it all depends on convolution, actually. All of this is based on convolution. That is important in its own, and we will discuss that when we come back from the break. Okay, I'll see you in 10 minutes. Okay, so let's get started. So I want to go back to this slide very quickly because I went over it really quickly, but this basically shows how you convolve these input features, different parts of an image, now that we've seen the image, with these convolution filters. These are essentially the weight vectors that you learned through training many, many images. And then essentially the convolution maps these input features by multiplying them with weights. In this case, basically, we express them as matrix multiplication somehow. You basically multiply these input features with these two different convolution filters, and you basically form some output features that are input to the next layer. Maybe you do some subsampling after that. Essentially, this is convolution. This is one way of expressing it. You can express convolution as a matrix multiplication, or you can do convolution just like the operations that were specified. If you go back over here, this is the convolution specification, mathematical specification of the convolution. And there's a lot of theory that goes into it, which clearly we're not going to cover. Okay, basically, we will see that we're going to implement a specialized architecture that does convolution directly in the systolic array. But you also imagine that you could do all of this matrix multiplication at GPU, and we will also see that in the next lecture. Or you could design a systolic array that does matrix multiplication, as opposed to doing just convolution. So there are many ways of actually taking the same problem and mapping it into hardware. Okay, one of the other things is actually, I will also mention, this also meshes well with what I said earlier. You're in a university, you have the potential to make huge impact like these guys who took the class from Andreas Moschowitz did, right? So they actually had a huge impact on the world by taking the class and saying, okay, we're going to accelerate this deep convolutional neural network, and we're going to go into this competition, and we're going to win it. And they actually did, and they wrote a paper. And if you look at this paper, I think this is cited by all papers in machine learning today. I don't know how many citations it has, but it could be more than 30,000. It's reaching the levels of Karl Marx almost, right? Marx is one of the highest cited scholars in the world, by the way. If you didn't know that, it's very interesting. Marx, Freud, those are relatively old, of course. This is 2012, right? Okay, anyway. It's good to think about the broader perspective, right? Okay. Okay, let's go back to convolution. Basically, it all boils down to convolution. And this is convolution. And in 1980, late 1970s, this is exactly what H.T. Kung at Carnegie Mellon University wanted to accelerate. He said convolution is important for many tasks, many image processing tasks, filtering, pattern matching, correlation, polynomial evaluation. We want convolution in there. And this is the architecture that he built, basically. It's very simple, very regular, and it's essentially, this is the processing element that we're going to use. It's not a processor, as you can see. What does it do? It basically does this function. It takes xin as input from the left side, and it has a weight that's installed in it. And what it does is it basically multiplies the xin with the weight and adds in to it. And y out, outputs y out in this direction. That's the calculation of the y out. And then it passes xin directly to the next element, so that the next element can use this data. Now, you connect three of these elements, and you get these functions. X is our input from the left over here. So you can see that x1 is here. While x1 is here, there's nothing here. You need to ensure that there's nothing here. x2 is input at this point in time. You need to ensure there's nothing in the next cycle. And then x3 is input in the next point in time. So you need to orchestrate the data flow such that the data flows from the left to the right. X is flowed from the left to the right. The processing elements do the right thing. And then y is from right to the left. And you get the outputs over here. Make sense? So what this element over here does is, it basically multiplies x1, w1, adds it to y1, assuming y1 is initially 0, you get W1, X1 over here. And then, when this is output over here, this X2 moves over here, you get W1, X1 over here, and then this element adds to that W2 multiplied by X2. Now you have the result W1, X1, W2, X2 over here. And once this is ready over here, X3 comes in over here. So you have W1, X1 plus W2, X2. And then this element multiplies W3 with X3. And then the result of Y1 propagates to the left. And that's what you get. And while this is happening, this is also happening, basically. You keep inputting X's from the left every other cycle. You keep inputting Y's this way. And then you can convince yourself by doing the calculations that you would get exactly what I said. So Y2, for example, will be W1. Whenever you input Y2 over here, every other cycle, you'll get W1 multiplied by X2. And then that will propagate over here. And then W2 will be multiplied by X3 by the time that propagates over here. So you'll add those. And then, of course, you have a continuous stream. X4 will come over here, and then you will multiply W3 with X4, and then Y2 will be output that way. Make sense? By orchestrating the data flow, if you have a continuous stream of X's, X1, X2, X3, X4, you basically input them every other cycle, and then you have Y1, Y2, Y3, Y4 going left. And you can imagine that if you have a billion X's and a billion Y's, and whatever number of weights that you have, you can keep doing this very, very efficiently. And all this element does is this function. It computes multiply and add. This is also called MAC, multiply, accumulate. That's a very common function that you use in matrix multiplication and many computations, convolution clearly, and also passes the data from the left to the right and passes the output from the right to the left. So you can see how regular this is, how simple this is, right? It's beautiful, actually. It's a very principled approach, again. But also, it's very powerful, because now you can imagine, okay, this is very, very specialized, but I can make it less specialized. I can add more weights over here. Maybe I can even make it a simple processor to operate on the data. This is very, very specialized, as you can see. Yes?
Are the weights fixed, or can they be changed by...
We'll get to that. That's a very good point. In this case, it's fixed, but clearly, if you want to be more general, you change the weights. Exactly, yes. Or you need to load the weights initially before, but people have later added more weights inside a single processing element. So if you want to actually accelerate machine learning, clearly you want to be able to load weights and have more weights to be able to do this. This is the simplest approach. And then, I'm not going to go through this, but one of the downsides of this approach is you can input data every other cycle, because multiply and accumulate are not overlapped. You can actually go and separate those elements and overlap, multiply, and accumulate, have a little bit more complexity, this sort of connection. And this way, you can input X's every cycle, as you can see over here. But you're going to read the paper, and you're going to understand this better. So it's worthwhile to design this adder and multiplier separately to allow overlapping of multiply and add execution such that your throughput doubles. Okay, so clearly, if you want to take advantage of this, you need to carefully orchestrate when data elements arrive into the input array, are input into the array. And this is the difficulty of programming this machine, actually, because you need to also ensure that the output arrives at the right time, and you need to ensure that it gets buffered. So this gets more involved if your computations become more complex. Array dimensionality increases, so if you want to do many, many more convolutions, or if you want to do different operations, as we will see, it becomes more complicated. And if the processing elements are less predictable in terms of latency, it also becomes more difficult. If everything is done in one cycle, clearly you can orchestrate when you should input the X's, right? And when you will get out the Y's. But if your latencies become more variable, not predictable, then you have a problem. So if you start adding loads into this, it won't work, because you cannot orchestrate the data very well unless you ensure that the loads take predictable amount of latency. Right? Okay, so these are some other examples. So you can see that this is a two-dimensional systolic array. For example, you can put the X's here and Y's here, and then do some multiplication. This is interesting also. And this is another interesting thing. It depends on the computation that you use. And I'm not going to go through this, but you can basically, this is one example. The choice of a 1 or 2-dimensional scheme is very dependent on how cells and memories will be implemented. And it's kind of obvious, hopefully. But you can read the paper. In fact, you should read the paper. Okay. So you can actually have combinations of these to build even bigger systems that can do acceleration of many important functions. So you can basically change them together to form more powerful systems. So for example, this systolic array over here is capable of producing on-the-fly least squares fit. Basically, you're trying to fit a function to the data, and you're using the least squares method. And you're basically doing it continuously while the data is arriving. So this is computing the least square fit to all of the data that has arrived up to any given moment. And you can see that the data is arriving this way. It's a matrix again. And let's see, given an n by p matrix X and a vector Y, determine a p vector such that something is minimized. That's the least squares minimization actually over here. And there are 2 steps that they take. So this matrix over here, this systolic array over here, does orthogonal triangularization. You don't need to know that, but you can learn about it clearly. If you're taking a linear algebra class, you've gotten the basics of this probably. And you basically take this output of the systolic array, have some elements for buffering, as you can see over here. These elements over here is to just ensure that the data arrives at the right time to the other systolic array over here that solves this triangular system with some mathematical equation. So you can see that this systolic array is very specialized to do orthogonal triangularization, and you need to orchestrate the data. So whenever x11 is input over here, nothing else is input. Whenever x21 comes over here, x12 should come. Whenever x31 comes over here, x22 should come. So you basically input the matrix this way, and the outputs, as you can see, are propagating that way. And then you need to get the final output over here. So it's pretty cool, actually. It's a very cool system. And it shows the power of this sort of specialized architecture. And this is very different from a von Neumann system, as we've seen, right? In a von Neumann architecture, you have instructions doing everything. These are not instructions, as you can see, right? These are functional units that are capable of doing stuff. And you're really inputting the data such that the data arrives at the right time to the functional units. They do their stuff, whatever stuff they're doing. They're specialized for the stuff they're doing. Clearly, convolution operations are one example of stuff. And you're orchestrating the data such that you get the right result at the end. So imagine now how you program this. When you program this, clearly you're not using instructions. You're really programming in a data manner. You basically say, assuming you designed this, of course, to begin with, how am I going to input the data into this such that I get the right output in the result? And that is the difficulty, because it may not be as easy depending on the structure of the machine. Okay, so let's talk about the advantages and disadvantages before we generalize more. So clearly, this was proposed to efficiently make use of limited memory bandwidth, and it does actually. It basically makes the most out of a single data element before it puts it back to memory, because the connections between processors can be very fast. It's specialized. Basically, it specialized the computation needs to fit the processing element organization and functions. That's good. It improves efficiency also, power efficiency, energy efficiency. That's one of the reasons why it's being used. It's not good for performance, it's also good for power. Yeah, I guess I don't have power. I guess efficiency is a very general term for everything. And you get high concurrency or performance. And it's a simple design as well. And it's always good to do more with less memory bandwidth requirements, because memory is a bottleneck, and this realizes it early on, such that you don't need to go to memory as much. So the downside is also, so the upside is specialized. It has a lot of benefits, clearly. But the downside is also it's specialized. Why? Because it's not generally applicable, because now your computation needs to fit the processing element functions and organization. The convolutional multiply and add, if you cannot map your computation to multiply and add, well, too bad, you cannot use it, right? That's not for you. Just go and find some other processor. Design your own processor. That's the downside. It's not generally applicable. But people have tried to make it more programmable, and we're going to talk about now branching out to other concepts that were inspired by this concept. So each programming element in a Systolic array, for example, can store multiple weights. Your colleague asked that question. You can actually store multiple weights. You can have a little bit more memory inside there. Now you can start selecting which weight you use. You can select the weights on the fly based on some input. Now you actually need some more input to decide which weight to use, of course, unless it's really purely data dependent, meaning maybe you check the data and then use the weight, but it's usually not like that. So this eases the implementation of many, many filtering mechanisms. Adaptive filtering, for example, you adapt the filtering based on the environment, and a lot of image processing tasks actually do that. So taken further, actually, the concept is actually much broader. Each processing element can have its own data and instruction memory. You can have data memory to store partial or temporary results or constants. And this leads to the concept of stream processing or pipeline parallelism. And you can even think of these as an early incarnation of multi-core engines, right? We're talking about 1970s. They're not thinking about multi-core. But the concept itself is so powerful that you can think of chaining multiple different programmable cores and then orchestrating the data movement across them such that you improve performance and efficiency. So let's talk about pipeline parallelism. This is, or more generally, this is called staged execution. I really like this concept because this is a very general way of parallelizing applications, and difficult to parallelize applications also. How many of you know about pipeline parallel programs? Not multi-threaded parallel programs, but pipeline parallelism. It's a special form of multi-threading potentially, but it doesn't need to have multi-threading. Anyway, let's take a look at it. I didn't expect you to know because it's not a concept. It's a more advanced concept. So basically, let's assume that you have a loop that looks like this. For I equals 1 to n, you have some stuff that you do in A, B, C. And for some reason, you thought that A would be good to separate from B and C and have different engines execute A, B, and C. Why could this be the case? Because all of the A's in different iterations may be operating on the same data. All of the B's may be operating on the same data. All of the C's may be operating on the same data. And there may be very little communication, data dependency between A and B over here and B and C. Whereas within A, you have a lot of data dependency. Within B, you have a lot of data dependency. And within C, you have a lot of data dependency. So this is one way of parallelizing a loop inside a single loop iteration. So one way of doing this is you basically split each loop iteration into 3 stages, A, B, C. And iteration I comprises A0, B0, C0. And you execute these on separate processors, let's say, or separate specialized processors. If you have a single processor, you execute on the single processor, and it's boring. It looks like this clearly, right? This is a single processor execution, A0, B0, C0. And then you go to the next iteration, A1, B1, C1. And then you go to the next iteration, A2, B2, C2. Clearly, an out-of-order processor overlaps the execution. That's not shown here, right? But maybe if you can actually parallelize the execution across 3 different processors, P0, P1, P2, even though they may not be specialized, they may be completely general purpose processors, you may get benefits out of that because all of the A's are operating on the same data elements, all of the B's are operating on the same data elements, and all of the C's are operating on the same data elements, and they're different data elements. This is a different data set compared to this and compared to this. Now they're on different cores, and now you can parallelize. A0 is executed in processor 0, B0 is executed in processor 1, and C0 is executed in processor 2, and all instances of A across all iterations are executed in processor 0, B's are executed in processor 1, C's are executed in processor 2. Now what we've achieved is we parallelized across the loop, right? Different iterations, each iteration still happens sequentially, so there's potentially some communication between A0, B0, and B0, C0. But the different iterations are hopefully independent, and you can actually parallelize the execution of A's, A1 and B0, A2, B1, C0, A3, B2, C1, and ... And if you have many iterations, now you successfully parallelize this loop by breaking it into stages. And now the next step is, of course, if you know what's going on in stage A, you can perhaps customize this processor to make it specialized for that. And maybe B is specialized for that, and maybe C is specialized for that. So maybe there's some convolution that's happening here. Maybe there's some reduction that's happening here. And maybe there's some, I don't know, accumulation that's happening over here, right? Now you can have specialized engines that can execute this code. So it's a very powerful concept, and this is called pipeline parallelism. And in this example, you see that conceptually, it takes about 12 iterations over here, or in a single processor, but it takes only 8 time units over here. This is, of course, conceptual, right? It doesn't take into account all of the factors like out-of-order execution. But basically, you reduce the execution time significantly. And these tend to be hard to parallelize applications. So basically, loop iterations are divided into code segments called stages. I'm going to go through this again, but in a hopefully simpler fashion. You have compute 1, compute 2, compute 3 stages, and you decide to put them on different cores. And you connect the cores with some queues. And you can do this in a threaded manner. Basically, you have a thread that executes all A's, and you have another thread that executes all B's, and you have another thread that executes all C's. I'm going to go through this quickly. There are real examples of this. So this is one example. If you're doing file compression, and if you want to parallelize it, you can actually break it down into different stages like this. This is a real algorithm that's used. You can, for example, allocate buffers in the first stage for some part of the data, and then you partition your data somehow, and then while you're reading input for the first part of the data, you're allocating for the second part. While you're compressing for the first part, you're reading input for the second part, you're allocating for the third part. While you're writing for the first part, you're compressing the second part, you're reading input for the third part, and you're allocating for the fourth part. ... Now this looks like a pipeline, right? But it's not an instruction pipeline, it's a higher level pipeline where you actually decompose your program into stages that are tied together, but each stage is now operating on a very specialized function. This can be specialized for deallocation, writing output, compressing, reading input, and allocation, right? So it's a very powerful concept. And this is also a systolic array, essentially. It's really not an instruction pipeline, but at some point, people start calling this pipeline parallel programs. This is really a systolic engine that takes the input file, an input file flows into the engine, and then data keeps flowing across different processing elements, and data keeps getting output. In this case, the data orchestration is simple because the problem is relatively simple, but there could be cases where the data orchestration is more complicated. Okay, so let's go back to systolic array advantages and disadvantages again in a different way. Essentially, what we're doing over here is we're making use of each data item many, many times. There's reduced need for fetching and refetching. You have better use of memory bandwidth compared to having a single processor doing everything, right? You decompose things into stages, and different processors do different things. And you get high concurrency as a result, and you have a regular design. Again, both control flow and data flow. But again, the disadvantages, very similar to the earlier systolic array we looked at. It's not good at exploiting irregular parallelism. Basically, it's very specialized. If your parallelism is not matching the structure of the hardware units that you have, you're not going to be able to do much. And it's relatively special purpose. Basically, you need software programmer support to be a general purpose model. It's not so easy. But it turns out there are many, many tasks. This is the warp computer. That's one of the first, it was actually the first systolic machine. H.T. Kung developed the idea, and he also designed the machine. This was designed for image processing tasks at that time. It was a linear array of 10 cells, and each cell had a 10 megaflop programmable processor in that case. It was not the very simple systolic array. It was attached to a general purpose host machine as an accelerator, very similar to the machine learning engines that we're going to see soon. And they designed the high-level language and the optimizing compiler to program the systolic array. So they wanted to hide this from the programmer. So the data orchestration is done, well, I guess they couldn't hide it from the programmer because the programmer still needs to code in a high-level language that enables the data orchestration to be done nicely by the compiler. And that was used extensively to accelerate vision and robotics tasks at that time, which were extremely taxing to general-purpose machines. And if you're really interested, you can read these original papers that talk about it. But the machine essentially looks like this. Is a host processor. You have some sort of interface, and essentially the X input is here, as you can see, and then you get the X back and the Y output back. And it was the processor array. It was a linear array, as you can see, with 10 elements in this case. And if you look into each of the elements, it was more complicated than what we've seen before for the very simple multiply and accumulate unit. As you can see over here, there's a memory, 32K by 32. It's a relatively large memory. So it's more or less a general purpose processor, except it's more specialized. And then you can see that the X inputs are buffered, and there's some buffering over here. Y outputs are buffered. There's some buffering over here. And address registers and, this is the, addition registers and multiplication registers. So this was actually still doing multiply and accumulates, but it could do multiply and accumulates in a much more general purpose manner. And you can see that you can store the intermediate results over here, and you could address also memory in some way, because you need to actually add, if you want to have more general purpose design, you need to actually get data from some other places, not just from the engine inputs and outputs. Okay, so this is a real example from 1980s. This is an example from 2017. This is Google's modern systolic array. They call it tensor processing unit. And you can read this paper if you're really interested. This is a real system that they use in all of their data centers, as far as I know. to learn from your data or anybody's data. Okay, I don't know what they do with it, but probably make money. Okay, basically, this is a systolic array. What they do is this is the heart of the systolic array. What it does is it does matrix multiplication unit. And you can see that they have buffers, very similar to something like this. Maybe it's a bit less programmable than this warp cell. And they have output buffers, and they essentially, the data flows this way, the partial sums flow this way. Basically, they do a matrix multiplication, x's and y's. They multiply two different matrices. And this is very interesting. They basically, they actually design the system such that the software doesn't need to do much. They say over here, software has the illusion that each 256-bit input is read at once, and they instantly update one location of each of 256 accumulator RAMs, whatever that means. Basically, they hide this from the software as much as possible, but they still need to do something in software to make to get the best performance out of it. But essentially, they convert convolutions or other operations that they need in neural networks into matrix multiplications, and this is a very fast matrix multiplication engine that operates in a systolic manner. And you can see that they also say the matrix unit uses systolic execution to save energy by reducing reads and writes of the unified buffer. Well, it's an old concept. As I said, this was designed for getting rid of memory accesses, right? And they exactly say the same thing. Okay. Figure 4 shows that data flows from the left and the weights are loaded from the top. So I don't know if figure 4 really shows that, but it kind of shows that, okay. You can read the paper for more detail clearly. The weights are preloaded and take effect with the advancing wave alongside the first data of a new block. Control and data are pipelined to give the illusion that 256 inputs are read at once, and I already said this. From a correctness perspective, software is unaware of the systolic nature of the matrix unit, but for performance, it does worry about the latency of the unit. What this means that you don't need to program the systolic array, but if you really want to get the most out of it, you need to somehow reorder your operations such that your throughput is maximized out of the systolic array. So they wanted to hide as much as possible, but they couldn't hide it enough to maximize the throughput. And the paper has a lot of interesting detail. So this is actually how it interfaces with the system. So this is really a general purpose processor on this end. It's the host in the warp processor. And there's a lot of control and data setup and buffering that you really, really need to do in order to be able to set up the data such that you can do the matrix multiplication. And all of this is necessary to hide this from the software programmer. And you can see that memory is also important because you need to input the weights from here and the matrix from here, and then you do the matrix multiplication. Okay, anyway, if you're interested, you can read the paper. It's not required, it's recommended, but this gives you a modern systolic array example. This is not the fastest. Actually, I don't know what's the fastest, frankly, but this is Google's TPU, second generation. So now you can see they add 4 TPU chips as opposed to 1 in a single thing over here. And they put it in a server machine, and then you can offload the tasks over here. And they use high bandwidth memory because the memory bandwidth requirements of matrix multiplication is quite high. They use floating point operations versus simple floating point operations, and their peak floating point operations per second, one measure of performance, is much higher right now. And they actually do not only, the first one was designed for inference meaning you've already trained the network, you basically input data and then get results out of it. You basically infer something, but they actually use this to train the network also. So that, they do a lot of backpropagation and all of that in this machine. So clearly there are other machines that are designed. Actually, maybe we'll put up some link to a YouTube video that Tesla recently released that talks about their own hardware design for their own, I don't remember what they called it, but machine learning accelerator, let's say. They have a machine learning accelerator also mainly to be used in self-driving cars. Actually, they may call it self-driving accelerator or something like that. So, and they are very clear that they designed it just for self-driving cars, and they actually customize this accelerator. They have a customized instruction set so that they can program this accelerator. And the goal is essentially to do a lot of convolutional neural network inference, because in a car, you really need to do this image processing, vision processing very quickly so that you can make a decision as to what should the car do, right? Where should it go? First of all, it needs to be extremely accurate. It needs to be extremely fast at the same time. It also needs to be extremely energy efficient because you don't have a lot of energy in the car, and you don't want to waste your energy on computing all the time, right? So their designs are actually also very interesting. It has a lot of systolic nature into it also. So if you're, we'll put up the video. If I don't think there's a paper that they've written, but their video is actually very nice because most companies don't like talking about these things, but their video actually gives a lot of detail, well, at least high-level detail as to how their architecture operates. But they also designed a complete instruction set, relatively simple instruction set to program their machine learning engine, and they also have a compiler that helps the machine learning. So you can see that all of these companies are actually doing the full system designs because the requirements of the application requires you to actually look at the problem from a full system perspective. You cannot just say, I buy the processor from Intel, or whatever, I shouldn't single out Intel, or I buy the GPU from NVIDIA, and my self-driving car will work correctly. Well, no, because your system requires something, some latency guarantees and energy guarantees that these other processors that you buy off the shelf may not be able to provide you. And they actually have very interesting performance results. I think they show that they're, I don't remember right now, but at least 7x more higher performance compared to the best previous competitor, according to what they claim to be best previous competitor. Okay, so that's systolic arrays. That's a beautiful story, I think. I think when I was teaching this course a few years ago, I didn't have the story. Now you get exposed to the full story. I would talk about systolic arrays, and systolic arrays are important, and it's important on many applications. And now, clearly, there are many, many more applications that are going to be important for. Okay, so we have time to cover one more paradigm. And we're going to shift gears. It's a completely different paradigm, but it's important to cover. And again, this is a paradigm that is not used a lot in existing systems, but it has some principles that are actually very good, in my opinion, that can enable systems to be much more efficient going forward. Let me give you the history. Basically, in the 1980s, people were implementing simple processors. Out-of-order execution was deemed to be too complex to implement, and also it had other problems like imprecise exceptions. And this was before Pentium Pro, clearly. Pentium Pro proved commercially that out-of-order execution, with all of the things that we talked about, branch prediction, heavy speculation, it's good for performance, and it was commercially extremely successful. But before that, people were thinking, can we get the benefits of out-of-order execution without paying the cost of out-of-order execution? And there's this beautiful idea called decoupled access and execute, which is kind of in between in-order and out-of-order execution. It has kind of a systolic principle in it also. That's why I like these concepts together. Basically, the idea is very simple. You have two processors, let's say. One of them is specialized for operand access, memory access, and the other is specialized for execution. And that's the idea. And they communicate with each other, basically. There are two separate instruction streams. These processors, the access instruction stream goes to the access processor, and the execute instruction stream goes to the execution processor. And they communicate with each other through queues. So queues are very easy. If you look at out-of-order execution, there are buffers everywhere. There's a messy interconnect everywhere, right? But if you want to communicate between memory and execution could be addition, for example, or multiplication, memory access, load, store. You basically have queue going from one to another, and then another queue going from the other to the first one, right? Basically, you have two queues. And you can have ISA visible queues also. So this is the pictorial view. You have the execute processor. It gets execute instructions, and it has a register file. And whenever it needs to do some memory access, it generates an address, and it sends it to the memory access processor. This is the execute to access queue. And then the memory access processor buffers some of these, and then does a read or write, and then sends the data back to the execute processor. So the beauty of this is now these can be completely decoupled from each other. This can make fast progress while this is slow. This can make fast progress while this is slow, depending on which one is a bottleneck, right? And these queues enable how much they can lag from each other. If you have, for example, a 1,000,000 entry queue over here and a 1,000,000 entry queue over here, this can be 1,000,000 instructions or whatever queue operands are there. This can be 1,000,000 instructions faster than this one, and you can still go ahead, right? Of course, I exaggerated, right? 1,000,000 is a lot. But, and there's also a branch queue, which is really the problematic part over here. And this is the paper that has introduced the idea. I'll very quickly go over the idea. Maybe you can defer the question to see if it still remains. So in the early form of the idea, the compiler generates two instruction streams, access and execute, and synchronizes the two upon control flow instructions using the branch queue. So this is one instruction stream, which we will not look at in detail, but it basically implements this code, which is some sort of scientific computation that was written in some vector machine at the time. And basically, you partition this code into access stream and execute stream. An execute stream, as you can see, does the operations, multiplication operation, addition operation, and puts the results, or gets the results from the queues, or puts the results into the queues, as you can see, right? And then it basically, for example, this operation is taking an element from execute the access queue, and or putting an element into execute access queue by taking an element from access to execute queue and multiplying it by x6. x6 is one of the locations. So these two streams communicate with queues, as you can see. So access stream, for example, it calculates an address, and it loads the data from a base address over here, and then puts the data into the access to execute queue. And then the access to execute queue can get the data and do the multiplication, and then it can keep getting the data from the queue. So it's very FIFO-based, first in, first out-based queue structure. So you need to orchestrate. The compiler's job or the programmer's job is to ensure that the right data arrives at the right point at the right queue. So in that sense, it's systolic. You still need to orchestrate the data movement, except now you have only two things to reason about. And it's very general purpose, as you can see. That's why the principle of systolic applies over here also. You still need to orchestrate the data. But these queues are scalable. You can have many, many entries. So what are the advantages? As I said, these can be decoupled from each other, as the name suggests. Execute stream can run ahead of the access stream and vice versa. If A is waiting for memory, execute stream can perform useful work. For example, if A hits in the cache, if it's not waiting for memory, then it supplies data to the lagging execute stream. And queues are very interesting because they actually reduce the number of required registers. Remember that when we're communicating, we use registers to communicate between instructions, right? Now, if you have this queue structure, and if you orchestrate the data in a first in, first out manner, and if you write your program such that the right instructions address the queue at the right points, you don't need registers. You just say, I'm going to get the data from the access to execute queue or execute the access queue. And you may have 1 billion entries, I'm just exaggerating, in these queues because they're really easy to build. They're just queues. They're not register files that need to be accessed in a random access manner. Queue access, as you know, is you just read the head, right? And then the head moves to the next one and input into the tail. So it's very simple access compared to registers. So that's why this is very scalable. That's why there's a very fundamental principled idea in this that is not being utilized very well in today's systems. Of course, this has disadvantages. Oh, okay. Before we go into disadvantages, what this enables is really what it's designed for. You have some limited out-of-order execution capability without the complexity of the wake up and select. So it doesn't go into all the way VLIW. VLIW says, I don't want any hardware support. Compiler does everything. Out-of-order says, I don't need any compiler support. If you give me compiler support, it's okay. I can use it, but I don't need it. But I can dynamically schedule everything. This is complex. VLIW is too simple, but compiler has a problem. This is kind of in the middle. It's basically saying, compiler, I need some of your support to partition these and orchestrate the data movement. But internally, I have these two processors that are going to help you so that I can tolerate some of the variable latencies that you cannot deal with really easily. And as a result, it's somewhere in between. So you get this limited out-of-order execution capability without the complexity of the out-of-order execution with Thomas-Low's algorithm. Of course, the disadvantage is now you still rely on the compiler. Not as bad as VLIW, but you still rely on the compiler to partition the program and manage the queues. And how good your compiler is determines the amount of decoupling that you have between access and execute streams. At some programs, it's very difficult. Some programs are just very difficult to partition. And in those programs, out-of-order execution does extremely well. Decoupled access and execute doesn't do too well. In some other programs where things are easier to partition and manage at the compiler level, out-of-order execution, you can get the performance of out-of-order execution at a fraction of the complexity without requiring going all the way to the VLIW philosophy, right? Okay, branch instructions are problematic. That's why branch prediction is so important in all processors, actually. Even VLIW, we didn't talk about that, but compiler needs to deal with branches somehow when it schedules the code, but we're not going to talk about that. That's a very messy issue. But branch instructions in this architecture require synchronization between the access and execute engines. Because if you get a branch in the access engine, then you need to ensure that the execute engine doesn't run too far ahead, right? That's why you have the branch queues. So one of the disadvantages that was solved later is you need multiple instruction streams. You need to partition your code into multiple streams, multiple threads, if you will. But this can also be done with a single instruction stream, as I will show you in a little bit. So this was implemented by this company called Astronautics. They actually did a lot of specialized processors. Very interesting. They're still around. I don't know what they do. Maybe some sort of screens, maybe, you can check. Basically, what they did was they had a single instruction stream. They had these access and execute pipelines. As you can see, this is the access instruction pipeline and execute instruction pipeline. In instruction fetch unit, they basically decide where to send the instructions. Clearly, access pipeline is specialized for access, and execute pipeline is specialized for execute. And they designed this based on some design criteria that they had. For example, they need an address unit over here. They had the floating point units over here, logical units over here. So this was their decision, basically. I think some of the integer instructions, for example, go into the access unit also. But they decided floating point operations are longer latency, so we want them in the execute unit. And this is a beautiful design also. I'm not going to talk about that more, I think. But there's a restart unit over here that ensures that things get synchronized whenever you have a branch misprediction. If you want to know more about that, you can read these works. So these, I don't want to go into compiler optimization that much, but I will talk about loop unrolling a little bit, because loop unrolling is a way of getting rid of branches. Does anybody know about loop unrolling? Who doesn't know about loop unrolling? Who doesn't care? Okay, nobody wants to. Maybe there's a hand over there, I see. Okay, you should care, because loop unrolling is a very, very effective technique to enlarge the scope of optimization and get rid of branches. So one example, this loop iterates n times. It's doing this boring accumulation. AI plus BI goes into AI, right? Maybe not boring, it may be very critical for Google to learn on your data, or your self-driving car to actually not crash. So basically, loop unroll, if you have a single branch after every one of these operations. Loop unrolling says, okay, if n is very large, I just do this. I just replicate the loop body multiple times within an iteration, right? As opposed to doing one of these operations, I do 4 of these at a time, and the branch doesn't need to be as frequent anymore. You have a branch every 4 operations. Of course, clearly now you need to have something special over here. You need to increment I by 4, meaning that basically there are multiple benefits here. You get rid of branches, and you also reduce the loop maintenance overhead. You're not doing the incrementing every cycle over here, right? Every iteration over here. You're doing the incrementing every 4 operations because you really unrolled 4 iterations into a single loop iteration now. So it also enlarges the basic block. So here, the compiler is limited by the branch, right? Or if you think about the decoupled access execute engine, it needs to synchronize somehow. But here, you have fewer branches. You do more operations before you get to a branch, which means that compiler can analyze the code without thinking about branches across here. And here I clearly show a very simple operation, but you can think of this loop iteration doing many, many things, right? Now the compiler can combine many, many loop iterations into a single iteration, and it can schedule code across all of those iterations. It can find the independent instructions. So if this loop iteration was 20 instructions, and if you unrolled it by 8 times, you would have 160 instructions over here. And the compiler could find independent operations much more easily across 160 instructions compared to 20 instructions. It could also do other optimizations without being hindered by the branch, because before the branch could be taken or not taken, but somehow it unrolled the loop. It could do some optimizations across the loop iterations, right? Which we're not going to talk about. You can watch the video. So the downside is, what if the iteration count is not a multiple of unroll factor? So you need extra code to detect this actually to work it out. But you can think about that separately. So this increased the code size. Very quickly, this concept is employed, decoupled access execute is employed at a very, very small manner in existing processors. What they do is they basically specialize different parts of the engine to memory versus integer. It's an example. but it's really not the same concept because there's no queue-based communication. But this is a very little incarnation of the concept in Pentium 4, and this is my own picture of Pentium 4, which I like better. Anyway, so that's the end of today. We're going to talk about GPUs and single instruction and multiple data next week. Have a good weekend.